Hello and welcome back to one more lesson, and this time we're going to talk about deflection. Very often, serviceability will govern the design of bending members. Therefore, we should do checks like deflection and vibration first before we go ahead and design the member for bending, compression, tension, bearing, everything else. When we carry out these deflection checks, we have to limit our deflection for several reasons. We talk about this topic in the lessons for roof and floor deflection, but just to summarize, we limit deflection firstly to prevent damage to brittle finishes. In residential buildings, plasterboard walls and ceilings are sensitive to excessive deflection, and excessive deflection leads to cracking, and cracked plasterboard is no good. Client doesn't like. So if you're designing a commercial building, let's say a warehouse or whatever other commercial building you're designing that has no internal linings, there's no plasterboard ceilings, and there's no plasterboard walls, you can allow for higher deflection limits because there's no brittle materials to worry about. Now the second thing is to keep visual appearance within limits so that the client doesn't crack the sheets and start annoying you. If a deflection is too noticeable and the client's walking past that member which is deflecting a lot, and every day that person is seeing that deflection, it's just gonna bother the client and they're gonna bother you. So it's better to limit deflection to prevent appearance problems. And then we want to prevent deflection of the roof so that the water rain doesn't pond and cause leakage. If you have a rafter and then it deflects too much, water is going to flow from the top and then it's not going to have enough power to go all the way to the gutter, and then it's just going to pond here in the middle, which could potentially cause leakage on the roof. And then the last thing is to limit the effect of creep, and we're going to talk about creep in a second. So if you head to our second brain in the deflection section, there are some examples or some specificities that might help you understand all these concepts that I'm talking about. For example, in the appearance problems, I talk about how a staircase going through a room could affect the perception of deflection. So have a read at this example about a staircase. Basically, I'll explain it to you very quick. So basically, when you look at a ceiling from below, the deflections are not so obvious. So at the moment, I'm looking at my ceiling above me. I can't really tell if there is excessive deflection. But if you look at a ceiling at your eyes level, then that's when deflections become more noticeable. And a situation that this could happen is that if you have a set of stairs going through a room, when the person walks down and up the stairs, when you are in the middle of the stair, and if you turn your eyes and look at the ceiling at your level eyes, any deflection of the ceiling will be much more obvious. But it's always good for you to understand these concepts, and then sometimes if you need to push the boundaries at some part of your design, you sort of have an overall understanding of where you can push the boundaries and where you cannot push the boundaries. All right, so to summarize, you can always ask yourself, first question, is there a line of sight along the member? Second question, will plasterboard or brittle materials crack? So if there's a beam holding a brick wall, I would be more stringent with the deflection limits. And then the third question that you can ask yourself is, will the doors or windows over or under be likely to jam? If the beam deflects too much, will it jam the door right below the beam? So that's something you have to ask yourself. Sometimes there is a glass partition over or under the beam, so you do want to limit your deflection so it doesn't crush the glass partition, right? Usually you have a clearance between the partition and the beam. Reduce section at connection points. We talked about this in the shear lesson, but I find important that you remember that if you reduce the cross section of the beam, let's say you had a notch at the support, or you were tapering the beam down to fit nicely inside the roof framing, for example. So imagine you have the roof line going down here on a pitch, then that means you can't continue that beam straight, because otherwise it's just going to protrude outside the roof sheeting. Therefore you have to taper that beam down. So since you watched the shear lesson, first thing that should come up in your mind is that you have a reduced shear capacity of these beams. Now you have to remember that it's not only a shear problem, it is also a deflection problem. Yes, you're reducing the section size close to the supports where the shears are high, so shear capacity could be of a bigger issue, but at the same time, if you are reducing the cross section of the beam, you are reducing the stiffness of that member, therefore you are increasing deflection. And this applies to any other material, okay? It's not only timber. If you reduce the cross section of a steel member, of a concrete member, the deflections will increase as well. So that's just something that you should bear in mind. For example, I recently did a renovation job, where we had to taper the beam down because it didn't fit inside the roof. So what I've done, I just model the ends of the beams with the depth, with the final depth of the taper. So the beam was a 300 PFC, and then at the end it went as low as 75 millimeters. So that's what I've done. I modeled the ends of the beam as 75, and that of course will affect the deflection of the beam if it was only 300 from one end to the other end. So by doing that, I was able to model a more accurate deflection calculation. If in this case it wasn't working, I would consider just drawing it as a tapered beam, because of course it's not 75 all the way, it's 75 only at the end. So it just it gradually tapers it down. So I could model this way, but in the end of the day it worked with just a 75 along the whole length of the tapered. So I was happy with that. Now let's talk about camber. To camber a beam, it means to curve it or arch it. So that helps to counteract the downward loads. So if you have a curved on the beam and then you have permanent loads, as soon as you put the permanent loads, the beam deflects to its normal state instead of just deflecting a little bit more than its normal state. When we go to Hein and then go to design, let's say Hein beam 15, you can tick the box use camber, or you can untick that box. If you tick that box, you have a beam 15 cambered, and if you untick that box, you have a beam 15 straight. So if you have a letter C as the postfix, it stands for cambered, and if you have a letter S for the postfix, it stands for straight. And you can purchase cambered glue lamps off the shelf, so that means you could possibly reduce the section depth of the beam that you're using if deflection governs your design. The deflection of a timber beam has two components. The first one is elastic deflection, and the second one is creep deflection. Elastic deflection is instantaneous deflection in response to any load. So it's basically the elastic theory that we study, which means if we apply a load, the beam deflects straight away, and if we remove that load, the beam returns to its original position. Now, creep deflection is a time-dependent deflection. So at the moment that you apply the load, the creep deflection is 0. But over time, the beam deflection keeps increasing even if we don't increase the load. If it's a time-dependent and we need this long-term load to be applied to the beam, that means that for short-term loads like wind or short-term live loads, they don't last long enough to cause creep effects. the loads are of very short duration. Let's say a wind gust is like 5 seconds. So there's no time for creep to happen. Now, creep is also dependent on the change of moisture content. That's why seasoned and kiln-dried timber are best for structural applications, because the moisture content in unseasoned timber tends to vary a lot. And that means that the creep deflection tends to be higher as well. If the member is painted, it will slow down the moisture movement, and therefore it will help with the creep deflection, at least temporarily. AS 1720.1 uses a duration of load factor called J2, and that is to account for creep deflection. So we know that the moisture content in seasoned timber is between 10 and 15%. So this first line is going to be for seasoned, and then we know that for unseasoned timber, the moisture content is over 25%. So the second line is for unseasoned. For bending, compression, and shear members, J2 factor can vary from 1 to 3. If we're dealing with, let's say, a permanent load and it's a seasoned timber, J2 equals 2. If it's unseasoned timber, J2 equals 3. If we go back to Hein, and then let's reduce this span, clear, and let's check a unseasoned F17 hardwood. Click design, go to report, engineering report, and then because it's unseasoned, let's find J2. Creep factor J2 equals 3, which is exactly this one, because we're talking about unseasoned timber. Now if we go back and change that to kiln dried hardwood F17, click design, go to report, and now the J2 factor equals 2. And this creep factor is multiplied to the deflection. So this number, J2 factor, means that when you calculate the deflection of a beam, if you find J2 equals 2, that means you double that deflection. If you find J2 equals 3, that means you triple that deflection. Oh, and another thing that I should have shown you is that if we scroll down to the load combinations, you can see that the J2 factor is only applied to the permanent load combination, right? If it's we're checking deflection, that means we have to check the load combinations for serviceability. And then we go down here and see that the J2 factor is only applied to where we have permanent actions in the load combinations. In this case, we have the G, which is a permanent action. That's therefore we have J2 equals 2. But then for the short-term loads, J2 equals 1. If we design a rafter, for example, let's say new member, let's go to roof rafter, design, clear, and then kiln dried F17, report. Let's go down to load combinations. Again, you can see that for wind loads, you don't apply the J2 factor, and for live loads, you also don't apply the J2 factor. It's only applied to the permanent load. Deflection calculation, you should be pretty familiar with this formula for a uniformly distributed load on a simply supported beam. That's 5 times WL to the 4 divided by 384 EI. That's your basic formula that every engineer should know by heart. But notice that for timber now we have the J2 factor introduced into this equation. And as I said before, that means if you have a J2 factor of 2, you double the deflection. If that J2 factor equals 3, you triple that deflection. So if your J2 is 2 and then you worked out the deflection of 10 millimeters, you can expect another 10 millimeters extra of deflection in that beam. So now you understand that the creep deflection, the long-term deflection of timber, is dependent on the moisture content of that timber, and also for the how long that load is applied to the timber. So if you can recall from our first lesson, we studied the K1 duration of load factor. Do you remember that? So K1 is for the strength check of the beam, and J2 is for the serviceability check of the beam. So they're both duration of load factors, but one is for the strength and the other one's for the serviceability. So that was it for this lesson. I hope you learned something new, and in the next one, which is the last one, now it's the last one of the overview of timber design, we're just gonna go quickly through combined bending and compression. All right, so see you in the next lesson.